starting. So happy to take it away.
Yeah. Okay. Everyone can hear me, okay? And let me make sure Eric is here.
Eric is here. Yes.
Oh, okay. Yeah, just making sure. Okay. Okay. So I'll start. Okay. So hello everyone. I think everyone already knows me here.
Just one quick question. I'm not sure if you can hear.
I'm going to talk today about some work on some commutative algebra. So this is joint work with Rafael and Nitin Saxena, who's at IT Kanpur. So the title of the talk is Primes via Zeros, Interactive Proofs for Testing Primality of Natural Classes of Ideals. So roughly speaking, the problem that we're going to solve is like this sort of algebraic problem of testing primality for ideals. And we're going to use some sort of geometric methods to solve this algebraic problem. Right? So that's what the primes via zeros part of the...
One thing, can you do either the iPad or the...
Okay. Yeah. Okay. Yeah. So that is what the primes via zeros part of the talk is, right? And we're not going to solve these for all ideals. We're going to solve these for some nice cluster of ideals. Yeah. Okay. So this is going to be the rough outline of the talk. Because the title has a bunch of things that I'll have to define. I'm going to do a bunch of background where I might talk about a bunch of stuff that is not related to the not directly related to the problem. After I do that, I'll state what the problem is, and then I'll discuss like some tools that we use. Some tools that will be important in the proofs, and then I'll sort of roughly go over what the proof ideas are. Yeah. Okay. Okay. So let's start with the background. Before I talk about the problem that we're interested in, let me talk about this other problem that should be more familiar to people, which is polynomial system satisfiability, right? So what is this problem? The input is a bunch of polynomials, f1 through fm, and they all have integer coefficients, right? They're multivariate polynomials in n variables with integer coefficients. And what you want to know is whether there is some common root of these polynomials, right? Whether there's some alpha bar such that all these fi's are 0 at alpha bar, right? So the answer to this problem depends on where you're looking for common roots, right? Note that these polynomials are integer valued polynomials, which means you can naturally interpret them as polynomials over any field or ring that you want, right? If you want to interpret them as polynomials in FP for some finite field, you can just go mod P with all the coefficients. So the answer depends on where you're looking for common roots. So here's like a few interesting places where you might be looking for common roots. If you want F2, if you want roots in F2 or some finite field, then this problem is NP-complete, right? This is like a canonical NP-complete problem. The certificate can just be the root itself, and you can check this in polynomial time. If you want integer roots, then this problem is undecidable. This is the famous Hilbert's-Tenth problem. It was proved to be undecidable in the 1970s. If you want rational roots, then we don't know how hard this problem is. Like we don't even know if it's decidable or not, right? So this is like completely open. If you want roots that are in the complex numbers or like the real numbers, then you can solve this in PSPACE, right? This thing should be surprising because the naive representation of any root is going to have exponential bit complexity. And it's possible that every single common root of your polynomial fi has exponential bit complexity in the input size, right? Which means a sort of a naive search or certificate for what a common root is over the complex numbers or real numbers, it's not guaranteed to exist, right? So the fact that you can solve this in PSPACE for these fields should already be sort of surprising, right? And the main idea is that when you start looking at fields like the complex numbers or the real numbers, there's like a nice algebra geometry, like there's a nice relationship between the algebra and the geometry, which lets you give PSPACE algorithms for this thing, for this problem, right? In fact, for the complex numbers, where this relationship between algebra and geometry is the strongest, we can actually solve this problem in AM, assuming this generalized Riemann hypothesis, right? Yeah, so basically for the rest of this talk, most of the results I'm going to state are going to assume this generalized Riemann hypothesis. It doesn't really matter what this is. For us, you can sort of think about this result as saying that the primes are distributed sort of evenly as expected, right? Like that's sort of the rough intuition. Like if you want a prime with a certain property, and you know it has a certain density, then you know that it reaches this density fast enough, right? So yeah. So and this was proved by Koiran in 1996. right? That for the complex numbers, you can actually check whether a system has a common root in AM. So AM is it's an interactive. It's the Arthur Muller complexity class. It's an interactive complexity class. Again, you can think of it as NP with randomness. So it's almost like someone's giving you a certificate. So if you think of NP as like someone giving you a certificate for the yes instances. Sorry, this should be CoM, by the way. The protocol is for the yes instances, and I've stated it for the. Oh, sorry, scratch what I said. No, this is fine. This is fine. Yeah. So the protocol is for the existence of a common root. So NP is like for the yes instances, someone gives you a certificate. AM is like there's some randomness involved. There's randomness both before and after you receive the certificate, right? Does that make sense? Okay. Yeah. So the key idea is that when you're doing things over the complex numbers, there's some nice algebra geometry that's going on that lets you solve this problem fast, right? And I spend some more time talking about what this relationship is, right? So again, we have this problem. You have a bunch of polynomials you want to take if they have a common zero. Suppose you could find polynomials G1 through Gm such that summation fi gi was 1, right? Suppose you could find such polynomials. Then if there was a common root to your original system, you reach a contradiction by evaluating this expression at that common root. Does that make sense? I don't know why I'm pointing there. I can just, sorry. Yeah. So by evaluating this expression, by evaluating this expression on both sides, you can reach a contradiction, right? So the existence of such polynomials G1 through Gm is a sufficient condition for there to not exist a common root. That makes sense? So there's this very famous theorem proved by Hilbert in 1893, which is that if you're looking for roots over the complex numbers, or in general over any algebraically closed field, this sufficient condition is also necessary. That makes sense? The only way polynomials don't have a common root is if you can write one as like summation fi gi. Does that make sense? In some sense, this gives you a way of proving that things don't have a common root, because now you just like your certificate can be these GIs. This almost works, but the issue is that these GIs are going to be too big, right? So yeah. Okay, that makes sense. This is called the Hilbert standards. Okay. So I just make a few. Throughout the thing, I'm just going to be trying to make a few definitions, like yeah, because I'll need them to state the main theorem succinctly. So I'll just define what an ideal is. This is one of the things that was on the title of the talk. So given polynomials f1 through fm, the ideal generated by f1 through fm is just the set of all polynomials that you can write as summation fi gi. That makes sense? Here the gi's are also themselves polynomials. Yeah. And once I've defined what an ideal is, you can restate Hilbert's Nullstellensatz as saying your polynomials f1 to fm have no common solution if and only if one isn't the ideal generated by f1 to fm. Right? This is exactly what the Nullstellensatz is. Okay. Okay. Let me make let me do another couple of definitions. I'll define the zero set, which is the natural thing. So for my polynomials, the zero set of my polynomials is just the set of all common zeros in Cn, right? I'm interested in the complex zeros. Yeah. So given an ideal I, the radical of my ideal will be all the polynomials such that some power of my polynomial lies in the ideal, right? The exact definition doesn't matter. It's just like, okay, you look at every polynomial that lies in the ideal. If it's some power of something, then I just add the root, right? That's what the radical ideal. That's what the radical of my ideal is. Why is this radical definition important? Because what Hilbert actually proved in his Nullstellensatz is something stronger than what I had on the previous slide. What he actually proved is that two systems of polynomials have the same zero set if and only if they generate the same radical ideal. Does that make sense? So if you give me two systems of polynomials and say, okay, these guys have the exact same zero set, right? It must be the case that they generate the same radical ideal. That makes sense? So in some sense, this is a bijective correspondence between zero sets in Cn and radical ideals. Yeah. Yeah. So this theorem is super important. It's sort of the start of algebraic geometry, which is like, I guess, an important field. Yeah. Yeah.
So, like, if you want to get the weaker version, you have to. It's one of like the two features of the zero.
So in the weaker version, one of these zero sets is the empty set. And the empty set is a common root of 1, just like the single polynomial 1. So if you substitute that in, you get the weaker version from this. That makes sense? Yeah. Okay. Okay. So yeah, the point of me saying this, making these definitions, is just to highlight the importance of radical ideals. So like amongst the class of all ideals, the radical ideals are sort of, from a geometric point of view, they're like very fundamental objects, right? They are equivalent to zero sets. Make sense? Okay. Okay. And now I can define what a prime ideal is. This was also on the title, right? So in general, an ideal is prime if whenever a product of two elements is in the ideal, one of them is in the ideal, right? H1 and H2 are two polynomials. If H1 times H2 is in the ideal, then either H1 is in the ideal or H2 is in the ideal. If my ideal satisfies this condition, I'll call it prime, right? This is the condition for general ideals. I'm going to be interested in radical ideals for this talk. So what does this primality thing mean for radical ideals? I know that radical ideals correspond to these zero sets, right? So I'll say that my radical ideal is this definition of prime ideal. If you sort of look at it geometrically, what it's saying is that radical ideals are prime if and only if the zero set is irreducible. That makes sense? And irreducible for me is something is reducible if you can write it as a union of like two other elements, right? I don't want to define irreducible formally, so we'll just sort of stick to an intuitive definition of what irreducible is, right? So, for example, this curve on the right is just one piece, so this is going to be irreducible. On the other hand, the zero set on the left is going to have three irreducible pieces. It's going to have this point and then these two curves. Is that good? Okay. Yeah. So can I repeat? Yeah. So I said this curve is one irreducible component. On the other hand, this guy is three irreducible components. Like one of them is this point, one of them is this curve, and one of them is this curve. Yeah. You also had a question.
Yeah, I get this, but how you're deciding?
So there is a formal definition, which is that if you an irreducible curve and any irreducible set, if you write it as a union of two closed sets, then one of them has to be equal to the original set. So that's a formal definition. But for that, I first have to define a topology and stuff, which I don't want to do here. So I'm going to stick to this. Yeah.
Stick with it. If we had only one polynomial, whether it's irreducible.
Yes. Yes. Okay. Yeah. In the special case when you only had one polynomial, if m equals 1, then whether or not it's irreducible is the same thing as whether or not the polynomial is irreducible. Yeah. Okay. Is that good? Okay. Okay. So now, yeah, I made some definitions. Hopefully, I convinced you guys that radical ideals are important, and it gave you some idea of how to think about primality, at least in this case that we're interested in. So now I can state what are the problem that we're interested in is. So yeah, the problem that we're interested in is simply primality testing of ideals, right? So the input to my problem is going to be a bunch of polynomials, f1 through fm. Again, they're going to be integer polynomials in n variables. And what I'm interested in is the ideal generated by this prime, right? Note that my polynomials, the inputs are integers, but the inputs, I'm going to think of them as an elements in this complex polynomial ring, right? The fact that they're integers just so that I can actually represent them on Turing machine. Right? Yeah. So yeah, this is the problem. And again, just to remind people again, for radical ideals, which is sort of the kind of ideal that I'm going to be interested in this talk, this primality is equivalent to the zero set being irreducible. Yeah. And also something that I mentioned on the previous slide, when m equals 1, this is equivalent to, so you only have one polynomial. This problem is equivalent to testing if that polynomial is irreducible, right? So in general, this is general. So when m is more than 1, this thing is generalizing this irreducibility testing problem for polynomials. Yeah.
For radical, I think what is that point in that statement?
if the ideal generated by that is radical.
Yes, sir. Yes, yeah. So, okay, yeah. So to clarify, when I say 4 radical ideals, I mean, if the ideal generated by my input is radical, then testing if it's prime is equivalent to testing into zero set is irreducible. Yeah. Okay. Is that fine? Okay, cool. Let's just see an example. So I have 2 possible inputs, right? One on the left and one on the right. In both cases, my inputs are 3 polynomials and 3 variables, right? And these inputs are pretty close to each other. The only difference is in the last equation, a couple of coefficients have changed by 1 or 2, right? So what do the zero sets look like? So it turns out that the first set of 3 equations, its zero set is going to be an irreducible curve. So these are going to sit inside 3-dimensional complex space, which I can't draw. So this is sort of the real part of the curve. And also it's in R3, which I can't draw. So this is like what R3 looks like from R2. Yeah. So the first 3 equations, their zero set is going to be one irreducible curve, right? By the way, those 3 equations are the twisted cubic. It's like a pretty well-known system of equations. They cause many problems. On the other hand, the second set of equations, which is very similar to the first one, its zero set is just going to be 4 points, right? One of these points is easy to describe, -1, 0, 0. The other points is going to involve some cube roots of -2 and something, right? But you can write down what the points are easily, right? So what this example shows is that by just changing the input very little, the zero sets can change massively. Like you can, on the one hand, you just have like 4 points, which is reducible. On the other hand, you have something irreducible and like it's a whole curve. That makes sense? Yeah. Right. 4 points are reducible because it's a point is for me is irreducible. So 4 points are unions of 4 point is a union of 4 points are a union of 4 points. Sorry.
Each isolated point is irreducible. Over that. An isolated point. If you draw one curve, if you draw one surface, think of those as irreducible. So when you say that the iris of physical irreducibility is only defined by an irreducible, that's over C.
That is over C. Yeah, that's over C. Yeah.
So is it like irreducible like minimal? You say like union doesn't mean that it's minimal.
In what sense do you want it to be minimal?
Okay, we understand.
Okay. Yeah. No. Yeah. So it's my fault. I don't know what a good way of doing irreducible is without doing the formal definition. So, okay. Is that fine? Okay. Okay. So let's just discuss a little bit about what previous work on this problem is. So the general case of testing if an ideal is prime without looking at special classes of ideals, this has been studied for a long time, for over like 120 years now. This first thing is like a paper of Lasker from 1905. And this is very hard, right? All the algorithms that we know for this problem, at some point or the other, they involve a Grosvenor basis, right? By the way, we know many different algorithms for this. These last 2 results are sort of the ends of long lines of work that use 2 different methods to solve this problem. I didn't have enough space to write down all the people that have studied this problem. But if you want to solve the general problem, all we know right now is that there's going to be some Grosvenor basis step. All the algorithms we know right now involve some Grosvenor basis step, which means in the worst case they're going to be X space hard, right? So solving the general problem is kind of hopeless, which is why we're sort of interested in natural classes of ideals. And for some nice classes of ideals, there are improved bounds. So if we consider radical ideals, which is like the focus of this talk, the classical works of Grigoriev and Tistov put this problem in X. And in 2007, Bugisa and Schreiblechner improved it to PSPACE. This is the best that we know for radical ideals. The other class of ideals that we study in this paper is this thing called complete intersection. For that class, the best we know is exp, right? Exponential time. And another interesting class is constant codimension, which you can think of as constant number of input polynomials, like M is constant. In that case, we actually have an efficient algorithm. If I is radical, then we can solve this in randomized XC time. right? This is also a result of Burgisser and Scheibler. So this is like just like a snapshot of what like the previous work is on this problem. Okay. And we also have some easy lower bound on how hard this problem is, right? So I'll describe the lower bound now. Let's start with arithmetization, which is a way of, so what is arithmetization? It's a way of starting with the Boolean formula phi, and then coming up with a system of polynomials, like let's say f1 to fm, right? It doesn't have to be a 3CNF, by the way, it can be any Boolean formula. And what does arithmetization do? It takes a satisfiable formula and it gives you a bunch of polynomials that have some roots, right? The roots will correspond to the satisfying assignments to your formula, right? So if your formula is satisfiable, you end up with a set of polynomials that have some set of roots. If your formula is unsatisfiable, you end up with a system of polynomials that don't have any common roots. Right? This is what arithmetization does. Yeah. We can just slightly modify this arithmetization process by just adding a point, right? So what I mean is, I'm going to take some Boolean formula. I'm going to look at the arithmetization, and then I'm going to slightly modify the equations that I get from that. What's going to end up happening is, if I started with something that was satisfiable, I'm going to have points that correspond to the satisfying assignments and one additional point. And if I started with something unsatisfiable, I'm just going to have that additional point. Does it make sense? Yeah. So the usual arithmetization? It gives you many polynomials. If it's a 3CNF, for example, you usually have like the x squared minus xi polynomials, and then you have like for every clause you'll add like a cubic polynomial. It gives you a system of polynomials.
You have one variable.
No, you have n variables, the same as a Boolean formula. Yeah, you have one polynomial per variable to ensure that there's 0, 1 usually, because in the arithmetization you start with something Boolean or minus 1, 1, depending on how you want to look at it.
So wait, it's like every multilinear polynomial.
Yes. Okay. Yeah. Yeah. So that's the usual arithmetization. So when I do arithmetization plus a point, I need to modify those polynomials a little. The number of polynomials or the degree won't grow a lot. But what ends up happening is that we end up adding this one extra point in both cases. Right? Okay, so if you start with something satisfiable, you end up with something that you know is reducible, right? Because you're going to have this extra point plus points corresponding to the satisfying assignment. And if you start with something unsatisfiable, you're only going to have 1 point, which is irreducible. That makes sense? And I guess the key point is that you can add this point in a way that ensures that the ideal you get is very nice. Like it's both radical and it's going to not only be radical, but it's also going to be in the other natural class, like this complete intersection thing, or not complete intersection, this Cohen-Macaulay thing, which I'm not defining here. The point is this ideal is going to be very nice, right? And this shows that my primality testing problem has a Cohen-P lower bound, right? Because I've gone from satisfiability to the complement of my problem. That makes sense? Okay. So I have like a Cohen-P lower bound, and like my upper bounds on the previous slide were like pretty high up. So what is our main theorem is that for radical ideals, we can actually do this primality testing step in the polynomial hierarchy. Right? And pretty low in the polynomial hierarchy. It's just the 3rd level. Yeah. So it's in the intersection of sigma 3p and pi 3p. And our other main theorem is that for this other nice class of ideals, which is equidimensional Cohen-Macaulay ideals, we can also do primality testing in the same level of the polynomial hierarchy. Right? Okay, is that fine? So we almost close the gap between our lower bound and and what we know as the upper bound. Is that good? Okay. Yeah. Oh, so I should also re-emphasize our results assume generalizing one hypothesis. We use some fact that like some primes are nicely distributed. So yeah. Okay. Okay. So let me just talk about some of the ideas that go into this proof. Right? Like what sort of tools we use to prove this. The main, or one of the main tools we use is this idea of mod P reductions, right? What is this idea? It's this idea that if I have these polynomials f1 through fm, and I want to study their common roots in Cn, right? Then these common roots in Cn are going to be related to the common roots of my polynomials in fp to the n, right? So yeah, the roots of my polynomial in Cn are going to be related to the roots of f1 mod p through fm mod p in fp to the n as p varies, right? So on the one hand, you have these complex roots. On the other hand, you have these roots in fp for a whole bunch of primes, and these two objects are going to be related, right? That's yeah. So this thing is like, again, it's an idea that's been used in math for a long time, and this is the thing that we're going to exploit for our algorithm, right? We can also just do some quick examples to sort of see what this thing looks like. These are like three very simple examples. The first example has three polynomials, and so like x minus 10, y minus 12, and xy. And it should be easy to see that they don't have any common roots, right? Because the first two polynomials force x and y to be non-zero, and then the third polynomial needs one of them to be zero, right? So they don't have any complex roots, but they have roots in like f2, f3, and f5, right? Because in these fields, essentially one of the equations will become x equals 0 or y equals 0. So you can have common roots, right? My second example is like a single polynomial. It has integer value roots, x equals 6 as a root, and it also has roots in fp for every p. Yeah. The third example is interesting. It's x squared minus 5. It has a complex root, like it has two complex roots, plus and minus root 5. And when does it have a root mod p? It'll have a root mod p for those primes where 5 is a square, right? And by quadratic reciprocity, this will be half the primes, right? So for half the primes, x squared minus 5 will have a root in fp. For the other half, it'll have a root in fp squared. It'll have a root in the field extension. That makes sense? So yeah, so these examples should sort of give you some idea that there's some relationship between the complex roots and the roots in fp. But it seems like these examples also show that there can sometimes be some bad primes where this behavior is not the same, right? Okay, just do some definitions too, so I can state the theorem easily. State the next idea easily. Again, you have some polynomials. Recall that z was what I was using to denote the zero set of my polynomials in the complex numbers. I'll use zp to denote my the common zeros of my polynomials in fp. Yeah, and I'll use zp bar to denote the common zeros in the algebraic closure of fp. For some reasons which we'll see, I'll be forced to talk about the algebraic closure of fp too. So this is what zp and zp bar are. So if you try and sort of formally prove the idea that I had 2 slides ago, what you can prove, it's not easy, it needs the null syntax. But what you can prove is that if you have a system of polynomials without any complex roots, right? So if your zero set is empty, then zp is empty for all except finitely many primes, right? This is sort of the phenomenon that we saw in the first example. We had an unsatisfiable system, and I had like 3 bad primes where it ended up being satisfiable. But then for most primes, it remained unsatisfiable, right? Okay. And if you have a system of polynomials where the common root is non-empty, so where you have common roots, then zp is not going to be empty for infinitely many primes, right? So think of the third example where we had like x squared minus 5. So the common roots are not empty, and we saw zp roots in half the primes, right? Does that make sense? So these two facts follow from the null syntax and some number theory. Yeah, Shevatarev. Actually, if you just want infinitely primes, you don't need Shevatarev. It's can be easier than that, but yeah. This is the non-effective version. What Koiran proved, the way Koiran proved that satisfiability over the complex numbers is in AM, is that he took these two statements and he found exact bounds on what this infinite set is, and what the infinite set is in the first case, and how many primes are there, what the density of the primes is in the second case, right? So what Koiran proved in his 1996 paper is that if your polynomials don't have any common zeros over the complex numbers, then actually ZP is empty for all except exponentially many primes. This set of bad primes, which in our first example was 3, like we had 3 bad primes, the set of bad primes is only exponentially big, right? For now, you should think of exponential as being small because we're comparing with double or triple exponential. So when I say something is only exponential, exponential is small, yeah, on the scale that we're talking about, yeah. Okay, so ZP is empty. For all except just exponentially many primes.
Sorry, but I said that we could interrupt. Exponential.
Yeah.
Exponentially, I would see something like logarithmic or d to the n. So n of d something.
And also the height of the coefficients matter. Yeah.
So how is that? So what's your how do you measure input? Dense or
sparse? My input is going to have the input parameters are going to be the number of polynomials, the degree, the number of variables, and the height of the biggest height. So it's the I never know which you call the dense of the sparse representation, but you don't pay for every monomial. Yeah. Yeah. It's like the Does that make sense? It's the SLP input. Yeah. So it's the SLP size.
So your denominator, the mixture, that's it. Oh yeah, okay.
Yeah. Okay. Yeah. Right. Okay. And the second statement is that if your zero set of your polynomials is not empty, then ZP is not empty for primes with at least inverse exponential density. Right. Again, think of exponential as being small. So inverse exponential is sort of big enough. Right. Our density is high enough. Right. Again, if you think of our third example with x squared minus 5, there the primes with ZP not empty was half. Right. And half is inverse exponential. Is that are these good? Yeah. This the title of the slide is HN in AM. The satisfiability over the complex numbers is also called HN, and it's also called the Hilbert-Smith. That's the decision problem, right? That's what this type means. Yeah. Okay. So what can you do once you have these two statements? What's the upshot? The point is now the gap between the two cases is big enough for you to invoke a Godot-Sessions set lower bound protocol to put this problem in AM. Yeah. Basically, the idea is that if your input polynomials did not have a common solution, then there's only a small set of primes for which you might accidentally see a common solution in FP. On the other hand, if your polynomials do have common solutions, then you're going to expect to see solutions in FP for many, many primes. Right? And this gap is big enough that you can distinguish between these two cases in AM. Right? That makes sense? So this is how Koiran proved that the satisfiability problem is in AM. Yeah. Yeah.
Like in this problem, how are these polynomials being presented to you?
So this is, you can think of straight line programs or any representation you want. Like all you need is you need to be able to evaluate the polynomials mod P. So any representation that lets you evaluate the polynomials mod P, you can think of that. Yeah. You need to be able to evaluate them fast. That makes sense? Okay. 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 Let's see how these and how this fits into what this problem that we're trying to solve. Right? Okay. Recall that when focusing on radical ideals, we're trying to figure out what the radical ideals are, right? And so for that, what we're going to do is we're going to think about how can a radical ideal be not prime, right? To figure out if a radical ideal is prime, we're just trying to detect whether it's not prime, right? Just figure out all the cases where it's not prime. Equivalently, since being prime is the same as the zero set being irreducible, we're just thinking about what do reducible zero sets look like, right? There's two. So this all the reducible zero sets, I'm going to divide them into two cases, right? The first case is this thing over here, where there's going to be many pieces of the biggest dimension, right? So my first zero set consists of two curves, and like the biggest piece that I have there is a curve. There's nothing bigger than a curve. So I have two pieces of the biggest dimension. That makes sense? My second case over here is where I have a surface and a curve, right? So in this case, the piece of the biggest dimension is a surface. Like a surface is like a two-dimensional object. So I have one piece that's two-dimensional, and then I have like some piece of smaller dimension. That makes sense? So every reducible zero set is going to lie in one of these two categories, right? It's either going to have two pieces of the biggest size or one piece of the biggest size and then many pieces, or more pieces of smaller size, right? So I need to be able to detect both of these cases. Yeah. Okay. Is that good? So if you have three pieces, for example, you'll either have two of those pieces will be of the biggest size, in which case I'll call it the first case. Yes, it's at least two, and yeah. I only drew two, but in fact, the number of pieces can be exponential. That's sort of what makes this hard. With finitely, with like the number of pieces can be exponential in the input size. Yeah. So when I say I mean at least two. Okay. Okay. So how do we proceed? Our first step is going to be to figure out the dimension of Z, right? And what is the dimension? It's just the dimension of the biggest piece in my zero set, right? For this, I'm just going to use an algorithm of Koiran from 1997, right? So again, for a reducible set, the dimension is just going to be the dimension of the biggest piece, right? So if I go back to this example, in the first case, my dimension is going to be 1. It's two pieces of dimension 1. In the second case, my dimension is going to be 2, right? My dimension doesn't tell me if I have pieces of smaller size, nor does it tell me how many pieces of the biggest size I have. All it tells me is that, okay, the biggest irreducible component of your zero set has so much dimension, right? Okay, so that's going to be the first step. I'm just going to use an algorithm. Also, I just want to point out that computationally, this is our most expensive step. If we already knew the dimension to begin with, we can solve our problem in Co-AM. Like the reason we're at the third level of the polynomial hierarchy is that this step is hard. Like I don't know how to do this fast. Yeah. Okay. My step 2 is going to be to deal with the second bad case, which is where I have components of lower dimension, right? And the way I'm going to do this is I'm going to use this notion of tangents, right? Yeah, just at a high level, what is a tangent space? You can think of a tangent space as being a linear approximation to your zero set at any given point, right? Which is sort of similar to what tangents do in like when you're studying analysis. So if I pick a point on my zero set, my tangent space is going to be like a linear approximation to what my zero set looks like over there. So if I pick a point on this curve, for example, my tangent space is going to be like just a line, right? If I pick a point on the surface, my tangent space is going to be like some two-dimensional plane, right? When your ideal is radical, there is this matrix called the Jacobian matrix, which is just the square matrix of second-order partial derivatives of your input polynomials, whose rank captures the tangent space at any point, right? So because of this, checking for whether you have a smaller dimensional component is like looking for a point where the tangent space is small, right? But this is some sort of matrix rank computation thing, right? I have this Jacobian matrix. If you give me my polynomials, I can compute this matrix of partial derivatives. Now I just need to figure out what the rank is at like some point. I just need to find a point where this matrix has small rank, right? So this is some sort of matrix rank computation thing. And there's some standard methods to convert this into a polynomial system, right? You want some minors to vanish or not vanish. That makes sense? So this case where you have components of smaller dimension, this for us is like sort of an easy case. We can just use this Jacobian along with some standard tools to reduce this problem to another instance of satisfiability, right? And we can just invoke Koiran. The hard case is going to be when your the hard case for us is when our zero set consists of multiple pieces of the highest dimension, right? So if you look at this picture, if you just suppose just the red part is the input, that thing consists of two surfaces. Yeah, just the red part is the input, right? So how do we handle this case? Our first step is going to be to reduce the case of curves, like one dimension. for which we're just going to use this tool called the effective Bertini theorem. I was going to spend some more time talking about what this is, but I don't think I have the time. So I'll just skip this. Essentially, by picking a random hyperplane, you can reduce the dimension of the problem that you're considering. And you can do this a few times to go down to the case of curves. The hard part here is that you have to ensure that the coefficients of your random hyperplane are not too big, because our bounds will depend on the coefficients later. So the tricky part here is to ensure that you can do this with easy hyperplanes in that sense. Okay. Once you're in the case where you have to distinguish between whether you have one curve or many curves, we're going to apply this mod p reduction idea again, right? So if you're doing something like Koiran, if you want to go mod p and use that to figure out whether you have one curve or many curves, what do you need, right? What we want is that if our original zero set just consists of one curve, we'll want ZP bar to be one curve for many primes, right? In some sense, the property of having just one curve, we want it to be preserved when you go mod p for many primes, right? Here, I just want to point out that we need to, when I'm talking about curves in FP, I can't talk about ZP. I need to talk about ZP bar, because ZP is just a finite collection of points. So it doesn't make sense for me to say ZP is a curve or not, because ZP is just going to be a finite collection of points, right? But ZP bar is infinite, so you can talk about it has topology and stuff, right? So yeah, the first question I have to answer is, if Z is one curve, then is ZP bar one curve for many primes P? And similarly, if Z is many curves, is ZP bar many curves for many primes P? Right? I need this to hold. I want this property of being one or many curves to be preserved mod P for many primes P. That's what I need. And now there's this new complication, which is, okay, if I know that ZP bar is either two curves or one curve, how do I do this? How does Merlin convince me that ZP bar consists of two or one curve, right? At the end of the day, I want an interactive protocol. So at some point, I only have polynomial amount of communication. So I can't convince, how do I convince someone that, oh, here's a bunch of polynomials, in ZP bar, they only define one curve. Right? Elements of ZP bar are not polysize, like they can lie in some large extension, I can't talk about them, right? So how do I detect how many ZP bar components I have while just staying in FP, right? That's another new problem that I have if I want to use this mod P idea, right? So sort of luckily for us, there are classical theorems that answer these questions in some sense. So this question about how to detect the number of curves via just FP roots, it's answered by these things called by this thing called the Langmuir bounds. I will talk a little bit more about these on the next slide. So there is some tool that will let me figure out how many curves I have using just FP roots. And the first two questions have a positive answer by this classical result of Bertini and Noether. But this thing is unsatisfactory because the number of bad primes you get from Bertini Noether is like triple exponential. So it's not good enough for us like computationally, right? The theorem is going to say something like, okay, if Z is one curve, then ZP bar is one curve for all except triple exponentially many primes. Right? And that's not going to be good enough for us. Like, yeah, because we're bounded, we only have polynomial communication. Does that make sense? Okay. Yeah. Okay. So we sorry, before we go, so we'll sort of have to improve on these two theorems. We'll have to make these bounds better. Okay. So what are these Langmuir bounds that I mentioned on the previous slide, right? So Lang and Weil proved this theorem that if you have an irreducible curve in FP bar, right, then your curve has P points in FP. That makes sense? So you have a curve in FP, which is irreducible in FP bar. The number of FP points is going to be P, right? And there's going to be an error term. This error term is like root P, and it has some other dependency on the input, but these will be small compared to P. The leading term is P, right? But unfortunately, for this Lang-Weil bound to hold, your curve needs to have this technical property. It needs to be FP definable, right? What this means is that there has to be some set of defining equations for your curve with all coefficients in FP. Know that the curve lies in FP bar, right? So potentially, maybe the defining equations of your curve all require you to use elements from like some extension of P. But if you can actually define your curve just using equations whose elements are in FP, then you can ensure that the number of FP points you have will just be P, right? That's what the Langmuir bound tells us. So what we can do is, so what this lets us say is that if ZP bar is irreducible, if it just consists of one curve, then my number of FP roots is just going to be at most P plus some error term. And if ZP bar is reducible, and it has at least two FP definable components, right? It has at least two components that satisfy this technical property, then the number of FP roots is going to be at least 2P with some error term. Makes sense? And now you see we have this like sort of P versus 2P gap, and this gap is going to be big enough for us to invoke this Gold versus settler-bound protocol again, right? So our job is reduced to showing that if originally I had one curve, then it remains irreducible for many primes, and if originally I had many curves, it becomes reducible for many primes, and a bunch of these components are at least two components are FP definable for many primes, right? That's what our job becomes. And that's our main, like an effective bound on this is our main technical result, right? I'm just calling it an effective Bertini-Noether plus FP definability result, right? So basically what we show is that exactly what I said we needed. If Z is irreducible, then ZP bar is irreducible for all except exponentially many primes. So this bad set is again single exponentially big. And if Z is reducible, then ZP bar is reducible and it has at least two FP definable components. And the set of primes for which this happens again has inverse exponential density. Right? Again, exponential is small, so these bounds are good for us. Okay? And I also want to point out that these bounds are sort of tight in the sense the bounds look like 2 to the poly input. You might be able to improve the poly, but you can't avoid the 2 to the you can't avoid the exponential behavior. Right? So in that sense, these bounds are tight. Right? I think we have something like 2 to the n cube. You might be able to make that 2 to the n square, but it has to look something exponential. Yeah. Does that make sense? Okay, I had a couple of slides on what things go. So what things go into this, into the previous technical statement. But I think I'm almost like I have like a few minutes left, so I'll just skip this and we can talk about it more later if you're interested. But yeah, so so yeah. So yeah, just to summarize, so just to summarize, what we studied is interactive proofs for primality testing of some natural cluster of ideals. And what we managed to do is that for these natural cluster of ideals, we managed to greatly reduce the gap between the upper and lower bounds. We almost make them up to like a couple of levels in the polynomial hierarchy. We show that these upper and lower bounds match. And our main technical result is this effective Bertini-Noether plus FP definability thing. So we managed to show that the set of bad primes for reducibility and irreducibility is small, assuming GRH. Makes sense? Okay. Okay. So yeah, I just want to end with an open problem. So there are some natural open problems, which is just, I said like, for these ideals, we can do primality testing. For what other ideals, we can do primality testing, right? That's like a natural open problem. But the more interesting sort of general meta problem that we're interested in, the reason we started studying this work is that in general, many problems in computational algebraic geometry and commutative algebra, the solutions to these problems involve some algorithm that involves Grosvenor basis, right? And as soon as you have an algorithm that involves a Grosvenor basis step, it's hard to say how long this thing is going to run, right? In the worst case, we have to assume, okay, the Grosvenor basis is going to take how much, like it's going to take like exponential time, or you need exponential space to run this Grosvenor basis. But ideals come in like many different shapes and sizes. Like many problems are easy on large classes of ideals. So what I find interesting is to try and figure out what makes these problems hard. Like, can we sort of identify what property of some ideal or what property of some input makes a given problem hard, right? This is sort of what I want to study. Like primality, sure, it might be hard in general, but I want to understand what makes it hard, right? And this work is sort of one way to study that is at least figure out where it's easy. Once you figure out where it's easy, you can sort of try and isolate what makes these things hard, right? So in general, I want to study this not just for primality, but also for many other interesting, any interesting problems in algebra and like computational algebraic geometry and computational commutative. Yeah, and yeah, I just want to end with that. And this is the first open problem I mentioned. Like, just try and figure out what other ideals can you do primality more easily in. We have some understanding. Just to say a couple of words, when your ideal is not radical or it doesn't satisfy these other nice properties, what you can have is these embedded components, which is your zero set can have multiplicity at some places, and it's hard to detect these embedded components in just PSPACE or something. It seems like to detect whether an ideal has an embedded component, we don't know how to do this better than X space. So this is this seems to be like the barrier to improving primality for general ideals. But it would be nice to see whether this has to be X space or whether you can do better. Okay. Yeah, thanks.
You don't want to assume GRH.
Yes.
Is there anything better than PSPACE or any of these?
No, I think even Koiran's, like the Hilbert-Nussbaum problem, we only know it in PSPACE if you don't assume GRH. So yeah, that's been open for like 25 years now. I don't know how hard people have been trying, but yeah, it's something that people bring up. Like I've seen it brought up a lot, but I don't know how actively people are trying to solve this. So there the application of GRH is for an effective Chebyshев density theorem to hold. At least it seems to me, based on what I understand, that effective Chebyshев density theorem that you need, it's almost equivalent to GRH. If you have to prove this, then you maybe have to take another route. You can't just adapt Koiran's thing and just try to get around picking the prime. You'll have to do something more clever.